1. We're really under pressure during this episode of Science Max. Compressing a gas till it's pressurized is how we can do this, and this, and to a lesser degree, this.
Help, I'm being crushed by all this pressure!
Pressure, today on Science Max Experiments at Large. Phil to mission control. Come in, mission control. This is mission control, Phil. We read you loud and clear. I would... Oh. Greetings, Science! Greetings, Science Maximites! Welcome to Science Max Experiments at Large. My name is Phil McCordick, and today we're gonna be building an air-powered rocket. Too difficult, you say? Nonsense, it's easy. It's not like it's rocket science. Hey, it is rocket science. Cool! Here's what you need. You need a bottle and a cork. Make sure that the cork fits nicely into the bottle, and then you need an air pump, because you can't have an air-powered rocket without air. And on this air pump, you need a pin, the special kind that you use to inflate basketballs or volleyballs or stuff like that. Now, what you want to do is push the pin through the cork. You might want an adult's help for this. Push it through until it goes through on the other side, and then make sure you get a good seal with the bottle. Now you're ready to launch your rocket with air pressure. But first, let's do a few other things. Take your cork and put it in a tripod launcher. You can make this out of pencils or anything you want, as long as it stands up nice and solidly. And then, of course, you want to decorate your bottle so it looks like a rocket. This is my rocket. Pretty good, right? So stick the bottle on the cork like before, like that. And then you stick the pin in the bottom. And what we're gonna do is we're gonna inflate the bottle with air pressure, and then it's gonna launch. Okay, here we go. You know, rocketry really isn't something you should do indoors. Come on. This was supposed to be a field. What's going... Why are there... Oh, it's in my shoe. Oh, this will do nicely. Now, don't forget to do this with an adult, and don't forget your safety glasses. Now set up the rocket in a nice big open area, and make sure it's pointed away from you. And then what you do is you pump the air pump. And it puts air into the rocket, which pushes down on the water, which will push down on the cork, until eventually... So, be Science Maximites and come up with your own rocket design. Try different amounts of water, different fins, even a different size bottle. Try it for yourself and see if you can get one that goes higher than mine just did. How did I get in? I think it was this way. Do you want step-by-step directions on how to build your own air-powered rocket? Well, don't worry. Everything you need is on our website.
All right, now it is time to max out our air-powered rocket. I've got Adam here. Hey, Adam.
Hey, Phil.
How you doing?
Good, how are you?
Good. Adam's from Logix Academy, and you guys go into schools and talk about science.
We do.
Fantastic. Do you guys do a air-powered rocket?
Yes, exactly.
Does it look like this one?
Looks exactly like that.
Oh, that's great. So how do we max this out?
So we want to add more pressure to this bottle to try to get it to launch a little bit higher.
More air.
More air.
Great, so what do we do?
So we're going to use one of these.
Ooh.
It's an air compressor.
Right, which works a lot like the bike pump, right?
Yeah, exactly.
Cool.
So we're going to have compressed air coming from here through this tube into underneath here.
Yeah.
And out that nozzle there, and you're going to put your bottle on top.
And out the nozzle
like
into
that.
the bottle, like that.
Yep, and now we want to be able to hold it in place. So we're going to have these little fingers here that are actually going to work to hold it until we want to let it go. So we're going to lock it in place.
Oh yeah, look at that. Totally locked.
Exactly.
And then what? How do we launch
Now,
it?
you're going to take this cord and go a safe distance away, and we are going to pull it.
And then we would pull it. Which one do you want to start with?
I think we should use this one here.
Okay, great. Now we put water in it, right?
Yep, you're gonna put water in there.
Why do we use water?
So the water is gonna act to push the rocket up into the air. The compressed air in here is gonna shoot the water out the back, and the water is gonna push on the rocket and make it launch. It's just to give it a little extra push.
How do I get it on there without spilling any water?
So just rest it next to the
Just go
launcher
fast?
there. Yeah, just go really fast.
Ooh.
There you go.
There we
a
go.
little bit.
Haha. And then
Lock it in place.
locking it in place. There's no
Okay.
air pressure in the hose yet, right?
Not yet, no.
First, we have to spool out the launch cord. So the air compressor has the compressed air in it. It's ready to go.
Yep, it's all ready to go. We just need to connect the hoses.
Adam, I've noticed it's snowing a little bit. Do you think that's any reason why we should stop?
I don't think so.
No, the science must go on. Blast shields down. Connecting hoses.
When we connect the air hose, the pressure from the compressor travels down the line and into the bottle. You can see the bubbles of air going in. Those bubbles are carrying more air into the bottle, giving it more pressure.
Here we go. 3, 2, 1. All right, there's the rocket. Let's do it again. Launching in 3, 2, 1. Woo! Nice. Success.
Success.
Nice. So, small bottle, worked really well. How do we make it bigger? I know, bigger nose cone?
I think a bigger bottle.
Oh, bigger bottle, yeah, of course, that's easy. How about this empty water bottle that we have now?
That might work, except that the top here is too big. I don't think it'll fit on our launcher.
Oh yeah, so what should we use?
A 2-liter pop bottle might work a bit better because it'll be about the same size.
Oh, that's right, 2-liter pop bottles have the same opening as these small water bottles.
Exactly.
That's great. All right, let's make a couple rockets out of 2-liter pop bottles.
Awesome.
Pressure happens when you squeeze something or compress it. Solids do not compress very well. I will demonstrate. Solid? Is it compressing? No, okay. Liquids don't compress very well either. You can demonstrate this for yourself by getting a plastic water bottle and filling it right to the very top with water and putting on the cap and squeezing. You'll find that you can't really squeeze the bottle very much. But if you empty out half of the water, no, don't pour it on the floor, and then put the cap back on the bottle and try to squeeze it, you'll find that you can squeeze it a lot more. That's because gases compress much easier than solids or liquids. Here's what's going on. Say this container is, well, any container, and these magnets are air molecules. Now I'm gonna put the magnets in pole to pole so they repel each other and wanna stay a certain distance apart, just like air molecules do. There we go, a container at normal gas pressure. Now watch what happens when I add more gas molecules. They start to get squeezed together. And if I add more, the amount of space that each one gets is less and less. Now this container is under a lot of pressure. These molecules really want to escape through the top of the container, but they can't because I'm holding them down. If I took something like this plunger and I pushed them down even more, now they're really under pressure. They want to get out, but they can't because I'm holding them in. Now watch what happens when I let them go. They all pop out the top, and the container has returned to normal gas pressure. That's what happens when we put gas in a container like this one. These containers that hold compressed gas are made out of solid steel because you need something really strong or it might explode if you put too much gas pressure in it. That's why these are only filled up by professionals who know exactly how much pressure it can take. That is the power of pressure.
Our air-powered rocket was working pretty well, but there's always room to max it out. In order to do that, we need to understand how it works. First, we fill the bottle almost halfway with water, then we add air to the bottle. The air pressure builds up, and the air presses down on the water. The rocket takes off when we pull on the release valve, which was blocking the opening of the bottle. Once that happens, the air pushes out the water. It's the water that gives us our thrust, so the water is very important. Once all the water is gone, the air escapes and the bottle returns to normal air pressure. But by that time, it's high in the sky. Now the plan is to use 2-liter bottles instead of regular water bottles to see if they work better.
Now we've made a few more rockets out of 2-liter bottles, and I'm gonna fill this one up with water, and we're going to fire it again and see what happens. Now, the idea is that these will work better because they have more volume, and more volume means we could possibly put more air pressure in. It's hard to know until you try it, of course. But the other reason why it might work better is 2-liter bottles generally hold carbonated beverages, which means they already have to be made a little stronger than regular water bottles because they have to hold in the carbonation, which is just like air pressure. All right, ready to go. Okay, here we go. You ready, Adam?
Yep.
Okay, blast shield down. Pressurize! 3, 2, 1. Let's do another one. And 3, 2, 1. Whoa! Wow! This is the superhero design rocket, which I'm very excited about. All right, Adam, it's going really well. But before we fire this next one, how can we make it bigger, better, and more awesome?
Get more pressure.
More pressure. How do we do that?
Well, we're firing at about 90 PSI right now.
PSI, pounds per square inch of pressure, right?
Yeah. So we could increase it.
We could increase it. So how, we're at 90 now, how high does the tank go?
Go to about 120.
120 PSI. Let's see what happens.
All right, let's do it.
Here we go. 90, 110, 120. Should we fire it?
Let's fire it.
Let's fire it. Here we go. 3, 2, 1. All right. Hey, actually it worked okay. There's just a piece missing here, but I think the bottle is still okay.
Yeah.
So, 2-liter bottle, full pressure. I think we can still make something even better, even more maxed out. What if we used an even bigger bottle? You know the 5-liter ones that you see on a water cooler?
Yeah.
You think we can use one of those?
Definitely. I think we could use that. We need to change the mouthpiece size
Yes.
to fit our launchers.
Well, let's do it.
Do it.
Help, I'm being crushed by all this pressure. A whole kilogram is being pushed down on every square centimeter of my body. 103 kilopascals. Actually, 1 kilogram for every square centimeter on your body is the exact kind of pressure that you and I are under at all times every day. We don't notice it because we're used to it, but it sounds like a lot, doesn't it? Well, it is. Here's an experiment you could do with a plastic bottle. Say at room temperature, there are 10 million air molecules in here. Doesn't really matter how many, but we'll say there's 10 million at normal room temperature. What happens if I heat up the air inside this bottle? This is warm water. What I'm trying to do is heat up the air inside the bottle because the air molecules, when they get hotter, move faster and need more room. So the 10 million air molecules are starting to escape out the mouth of the bottle and reducing the number of air molecules inside. And now I take the bottle out and cap it. Because the air molecules heated up and speeded up, they needed more room. Now there's less of them in the bottle. There's about 4 million air molecules inside this bottle, but they're all hot air molecules and they have a higher pressure, and you don't notice it because the air out here isn't crushing the bottle. But watch what happens if I cool the air inside the bottle. This is ice water. So what's happening now is the molecules are slowing down and they need less space. So they need less room and they're being crushed by the pressure on the outside of the bottle. Ha-ha! It has been crushed because the colder air molecules don't need the same kind of room as the hot air molecules. The room temperature air has crushed the bottle. The air inside has a lower pressure than the air outside. Pretty amazing. Even more amazing when we max it out. This is a steel drum. What we've done is we put some water in it and we're heating it up to boiling so there's nothing but hot air inside the drum. This is an airtight cap, which we use to seal the drum. And now we cool the drum off. Hey, Trevor, give me a hand. Ready? 1, 2, 3, you lift! That's good. This pool is filled with ice. What we're doing now is cooling off the steel drum, which will cool off the air inside it. Which means, eventually, the air inside the steel drum will be a much lower pressure than the air outside the steel drum.
Because the steel drum has a lot more volume than a 2-liter pop bottle, it takes a lot longer for the air to cool down. The other thing to think about is that it's a steel drum. I could stand on it and it wouldn't even dent. But sure enough, after a few minutes...
Whoa! Check it out! The barrel has totally crushed. The low pressure air inside the barrel wasn't enough to withstand the force of the regular air pressure that you and I walk through every day. The air pressure all around us is enough to crush a steel drum. How cool is that?
Our air-powered rockets have been working really well, but we still want to go further. Since the 2-liter bottle worked better than the water bottle, we think increasing the size again might make it more awesome. So now the plan is to switch our 2-liter bottle with a 20-liter water cooler jug and make a rocket out of that. Because the launcher nozzle, which holds the bottle in place till we're ready to launch it, isn't going to fit the opening of this bigger jug, we've decided to use the cap that came with the jug. If we screw the cap on, it'll work sort of like the cork. The air pressure will press down on the water and keep pushing against the cap until the cap has a catastrophic failure, which is a very cool way of saying that eventually the cap will break and the bottle will shoot into the sky.
20-liter water cooler jug filled with some water. This is the cap that'll work sort of like the cork. We put the air pressure in there, the cap can't take it anymore, pops off, and the thing flies, hopefully. Let's find out. Okay, that looks good. There. Let's do this. Go for pressure! Uh-oh. Uh-oh. Oh, no. Hilarious! That worked pretty well. It sort of does that. I wonder if it's aerodynamic.
No.
No. So, what else can we do to make it even more maxed out?
I think we've used the 2-liter bottles that worked really well.
The 2-liter bottles are the best, right?
I think so.
So, what do we do?
We can probably stack them. We stack them on top of each other.
Yeah.
That worked.
I like that. So we put a whole bunch of them together.
Yeah.
Tell you what, I'll do you one better. Why don't we use 3 stacks?
Awesome.
We'll use 3 stacks, 3 launchers, 3 times the thrust, and we'll make a giant rocket out of 2-liter bottle.
Yeah, great idea.
High fives. Here we go. Gas molecules get further apart when you warm them up and closer together when you cool them down. So what happens if you keep cooling them down? Well, they turn into this. This is liquid nitrogen. Nitrogen makes up 78% of the air we breathe, but when you cool it down to minus 196 degrees Celsius, it turns into a liquid. It's boiling right now because at room temperature, nitrogen wants to be a gas. So the liquid nitrogen is turning into gaseous nitrogen, and all of the extra molecules are escaping through the top of the bottle. So what happens if I put a cap on the bottle? Right now, the liquid nitrogen is turning back into a gas, but because there's a cap on the bottle, the gas has nowhere to go. So the pressure is just gonna keep building and building until the plastic bottle can't contain it anymore, and it pops like a balloon. Science!
Our rockets have gone from small to bigger to even bigger. Now the plan is to use 3 2-liter bottles and create columns of them into a giant rocket. We pressurize them just like we did before, but with more thrust, it might work even better. Even if it doesn't work better, I'm pretty excited about this new plan.
Giant rocket! rocket. You ready?
I'm ready.
Okay, blast shields down. Connecting hose. Dialing up pressure. Pressure is rising. It's bubbling. Bubbling. 100 psi. Okay, stand by to fire. 3, 2, 1. Whoa! Woo! Awesome! Yeah, let's go check it out. Well, there you have it. Rocket Science Max. Experiments at large. Well done. Nicely, nicely done. Do you think we could fire it again? Yeah, it looks like it needs some repairs, though. Science Max! This episode of Science Max is all about storing energy and releasing it. Yeah, let's try it out for real. Storing it in a giant spool racer, plus a domino chain reaction, mousetrap chain reaction, popsicle stick chain reaction, and more. All on this episode of Science Max Experiments at Large.
Okay, 3, 2, 1, go!
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. Wow, I really need some more energy. Fortunately, I have some saved up. Ah, that's better. Yeah, I know what you're thinking. Storing energy like that doesn't make a whole lot of sense, but you can store energy, and that's what this episode of Science Max Experiments at Large is all about. In fact, I'm gonna store some energy in this container simply by putting it up here on the top shelf. More on that later. But right now, let's look at another way that you can store energy and release it in a really fun way. We're gonna make a spool racer, and it's pretty simple. Here's all you need. You need some science ribbon. Now, if you don't have science ribbon, you can use regular ribbon, but the ribbon really isn't important. It's the spool that's important. You'll also need a washer, elastics, pencil or pencil crayon, popsicle or craft stick, and science tape. Science tape is the same as invisible tape, except I use this one only for science. Here's how you build it. Break the popsicle stick so it's smaller than the diameter of the spool. Then put the elastics on top of the pencil and pull them tight. Thread the popsicle stick through and feed it all through the hole of the spool. Grab the elastics on the other side and pull out the pencil, and everything will be threaded perfectly. Then stick on the washer and thread the pencil through. Finally, tape the popsicle stick down so it doesn't move. And if any of these steps are a little too fast, don't worry. All of the instructions are up on the website. That was cool. I can't make it go away. I can only make it come up. So there you go, a spool racer. And here's how it works. You spin the pencil around, and that twists the elastic. Now that elastic is gonna wanna unwind, right? So just keep spinning that pencil around until it's good and tight. And then when you put it on the ground, the pencil's gonna wanna unwind, but it can't because the table's in the way now, which means that the energy is gonna transfer to the spool, which is gonna turn, whoa, and it's gonna drive away. Yeah, let's try it out for real. So why does this work? It works because the elastic is coiled, right? Yes, and because I'm putting in the energy to twist it. You see, I'm putting in effort to spin this pencil crayon around, and then when I've finished, all of my effort has been stored in the elastic. When I let it go, my energy transfers into movement. So that's, that's what we're gonna do today, Science Maximites. We're gonna max out the spool racer. I think Anthony would really know how to help me with this. So, I'm off to the Ontario Science Center. Come on. Phil! What happened? Phil! What happened?
You okay?
Anthony!
Yeah, hi.
Oh, were you in the middle of something?
Don't worry about it, yeah.
Oh, okay. Sorry about that. You know what, I was wondering if I could get your help with something.
Sure, yeah.
Yeah, one word. Spool racer. Actually, that's two words. Spool racer. Yeah, you want to help me max out a giant spool racer?
Yeah.
Awesome, let's go back to Science Max headquarters! Okay, Anthony, today I want to max out the spool racer.
Awesome.
right? So you twist up the elastic and it goes from potential energy, all stored, to
Kinetic.
kinetic energy.
Whoa.
There we go.
Awesome.
So,
Okay.
not too hard to design. Should be fairly easy to
Yeah,
max
really
out.
simple couple of parts here. We just got elastic band inside.
Yep.
And then this big long pencil to store the energy and then release it.
And the most important part
Is spool.
is the spool.
Exactly.
And I know where we should start.
Where's that?
Right here. This is an industrial cable spool. So the big, thick electrical cables, they come wound on this thing.
Yeah, okay.
So I figure we start with this.
Got
right?
it.
And the good news is that it's got a hole already. And check it out, it rolls really well, right? Okay, cool.
Okay.
So,
guess-
bungee cord.
Yep.
And long pole or something.
Yeah.
And we're ready to go.
I guess let's get some parts.
Okay.
Okay.
Oh, hey, how you doing? You want to buy something? I got a lot of stuff here, and I got a special today only. Potential energy, huh? I will throw in some potential energy with any order. You see this stuff on the shelves here? The stuff on the higher shelves has more potential energy than the stuff on the lower shelves. Don't believe me? Here, hold on. Look at this state-of-the-art traffic controller. Right now, it's sitting up here on this high shelf. Now, if it were to fall, it would be going fast, which means it would have a lot of kinetic energy. You see, when it fell down, it had enough kinetic energy to completely break itself apart. Yeah, well, that's the difference between potential energy and kinetic energy. Look at this bagel, just sitting here, not moving, minding its own business on top of this ramp. It's all potential energy and no kinetic energy. And when it gets to the floor, it's all kinetic energy and no potential energy. Woo! And now it has neither because it's on the floor and it's not moving. 5-second rule. And now you know your energy. So what do you say? You want this thing? Tell you what, I'll give you a discount because you know it's gently used. Hey, I'll even throw in this bagel, huh? Also gently used.
Anthony and I are maxing out the spool racer. We start with a long coil of bungee cord, which is kind of like a giant elastic, and feed it through the spool. Then we put on a big piece of plastic to act as our washer and use a long pole as the pencil. We flip the spool on its side to wind it up. Then we flip it back and it's ready to go.
All right, so we have it all wound up and we're ready to try it again, but with one change.
Phil,
Yeah,
what's with the trike?
I ride the trike.
It's like I always say, what's the point of building something big if I can't ride it?
There's no way you're gonna fit on this thing.
No, I don't put my feet on the pedals. I put my feet here on the back, right? And then-
Okay, yeah, I get it. You got it?
Hold on, I gotta do my helmet up.
Safety first. You ready?
I'm on it.
Okay, 3, 2, 1, go.
Oh, it's working.
It's working. Amazing.
All the stored energy in the bungee cord is being released and the spool starts to turn. There's even enough energy that I can get pulled along behind it.
It's not going that fast, though.
No, and it's-
pretty good, though. It still pulls me, right?
Yeah, pretty good.
So, Spool Racer, actually able to get pulled by it.
Yeah.
You know what? I think we can go even bigger.
Bigger.
Yes.
Well, what did you have in mind?
I'm glad you asked. Yeah!
What is this?
This is an industrial cable spool, and this is the biggest size that they make. And I thought we would do the same thing with this. What do you think?
I think this could generate a huge amount of energy.
Okay, so all we gotta do is just build it just like we built that other one.
Just bigger.
Except way bigger. Let's do it. When you set a domino on its end, you're giving it potential energy because it can fall. Ooh, and when you put two dominoes together, you can start a chain reaction. because that one will fall into that one. But it's a lot more fun with more dominoes.
Setting up a run of dominoes is a lot of fun, but it takes a flat surface and a steady hand. And if you want to do it yourself, add gaps, so if one part falls, it doesn't take out the whole run.
Last one. There. I had some dominoes left, but I did it. I made the Science Max logo. See?
Science
right?
Max!
Sort of. Let's see how it works. Ready? Yeah! Now it's time to max it out. Giant maxed out dominoes! Woohoo! Even though these dominoes are giant, they're still gonna work the same. They're standing up on their ends, which means they've got some potential energy. And when I give this one a push, that potential is gonna turn into kinetic energy, and it's gonna knock the next one, and the next one, and the next one. I hope. I don't know what's gonna happen, but let's find out. You ready? Okay, 3, 2, 1. Giant dominoes! Yeah, science! The problem is, when you use dominoes this big, setting them up again is a real chore. This is a mousetrap, but don't worry, no mice are gonna be harmed in the making of this episode. Mousetraps are a great example of stored energy. You see, in order to set a mousetrap, you have to push this bar back, and it's hard to do because the spring holds it. And then you set the mousetrap by putting this little lever underneath this very sensitive trigger, and once you have it set, all that energy is stored as potential energy, but it'll go off with just the slightest touch, releasing the energy. So what if I had a number of mousetraps and they're all set and all of that potential energy is stored up, and I dropped a number of ping pong balls on them? Well, then I could set off a chain reaction where one mousetrap flies and hits another mousetrap that hits a ping pong ball, and then they all go. Now, this is something you can try at home, but do not set the mousetraps yourself. It can really hurt if it snaps on your fingers, so you should probably ask an adult to help you, and then you can see how brave the adults in your house are. Okay, you ready? Here we go. Mousetrap chain reaction. And last one. There we go. And now, let's max this out. Let's do it with 90 mousetraps. And this is a crate of ping pong balls. So let's see what happens when we put them together. There you go. Maxed out ping pong ball, mousetrap, chain reaction. Awesome.
Ready?
I'm on it.
Anthony and I have built a large spool racer.
Oh, it's working.
It's working.
And it worked so well, the only option was to go bigger.
What is this?
This is an industrial cable spool, and this is the biggest size that they make.
I think this could generate a huge amount of energy.
Building our giant spool racer is the same process as the other builds.
So the steps are exactly the same, but on a larger scale. And this time we're gonna use, obviously, the large spool, and we're gonna use this 2x4 as our pencil windy thing.
Coil some bungee cord, feed it through.
Ready?
Yep.
Okay, here it comes.
There we go.
Got it?
Haha, yeah.
Add a washer and a long 2x4 to act as our pencil.
And now we stick the giant 2x4 inside the coil.
Just about. Yeah, we got it.
There
Okay,
we
cool.
go.
And we're ready to try it out.
So it looks like we're ready to go.
Yeah, exactly.
Do you want to do it in here or you want to do it outside?
Oh, definitely outside.
Okay, let's go.
Yeah, okay, cool.
Yep. Oh, it's heavy. Back batteries are great at storing energy. They store electricity. Batteries? But if you're like me and you have a whole bunch of batteries and you don't remember which are the good ones and which are the dead ones, there's a trick that you can use to find out. Get a frying pan or a brick or concrete floor or something else that's very, very hard and an adult's permission. Here's the secret. Dead batteries will bounce and batteries that still have some life in them won't. Watch. Good battery. Dead battery. Now, it's a little hard to see, but listen. 1 hit, 2 hits. Here's what's going on. See, batteries store electricity in the form of a gel, sort of like modeling clay. This is modeling clay, fresh from the fields, where the pits, the mine, wherever modeling clay comes from. And this is modeling clay I've left out for about 5 days, so it's all dried up and hard. Now, when modeling clay is new, it's all wet and soft, and when you drop it, it doesn't bounce very well. I've left this piece of modeling clay out to dry for about 5 days. Now it's all dried up and old, and it bounces. New, old. So, same thing with the battery. Good batteries won't bounce, and bad batteries will. Science. Here's a fun chain reaction you can do with popsicle sticks, or craft sticks, because these ones are a little bit wider than popsicle sticks. It is because these kind of sticks are slightly bendy, and when you bend them and put them together in a pattern in a certain way, you can keep them under tension, and then they want to snap back, and then they'll fly. So here's how you make the pattern. Ready? You take a popsicle stick or a craft stick, and you put it down on the table. I know, okay, it's a slow start. Then we take another one and put it across. Now comes the secret. The secret is over and then under. You want to put it over one and then under another, like that. And then this one, over, under. Put it over the one that looks like it's the top stick and under the stick that looks like it's the bottom stick. And then it starts to hold tension. It starts to hold the potential energy.
Continue this pattern. Each stick goes over and under the 2 sticks at the end.
Now here's the trick. Soon as this one lets go, then that one will let go, then that one, then that one, then that one, and that's how you get the chain reaction. They all start flying up. So you have to build it with never letting go of that last stick. You gotta always remember to keep a hand on it, or else you'll have to start again. So, okay, so you ready? You wanna see me let it go? Here we go. I know, that isn't so great because it's better if it's a longer chain. So fortunately, I have a longer chain. I've got a binder clip on this end, keeping the craft sticks together. Ready? 3, 2, 1. Wow! Release of kinetic energy from the potential energy of winding all the craft sticks together. Fun, and you can totally do it at home. Now, let's max it out. Behold, almost 800 craft sticks in a long, nicely designed triangle. Ready? 2, 1. Yeah! Craft stick chain reaction. I'm gonna go get something to clean this all up with.
All right. So Anthony and I have built a giant spool racer and have taken it outside to try it out. In order to wind it up, we flipped over the last version on its side. But this spool weighs 200 kilograms. Easy to roll, almost impossible to flip over.
Come on, get it.
I don't think it's gonna work. It's too heavy to move.
Yeah.
We should have thought of that before.
Well, I'm sure we'll think of something.
So Anthony and I thought about it. And thought about it. And thought about it.
I got it.
What?
But you,
And the answer finally dawned.
what if we roll it this way? Because then that would wind it up, right?
That's brilliant!
By rolling it backwards, we wind up the bungee cord in one direction, which will make it want to unwind in the other direction. Anthony and I roll it across the parking lot to get it wound up tight.
I don't think I can hold it anymore.
Okay. Okay. Let go. Okay, it's wedged.
It worked.
All right, one more thing. We're gonna hook the trike up to this one as well.
Okay.
Okay. So right now, it's all wound up, and when it gets moving, the potential energy in the coil will turn into kinetic.
Exactly.
Kinetic energy. Now, just in case you're tempted to try this at home, I need to tell you, do not try this at home. We're trained professionals, right?
Yes.
Yes. Well, as much as anybody can be trained for this, because no one really does this.
Are you ready?
Ready?
Okay, here we go.
Whoa. It's working.
It's working.
Yeah.
Sure enough, all the potential energy we stored in the bungee cords starts to unwind, which rolls the spool and pulls me along behind it. What's more, that big heavy spool has a lot of momentum. So when it gets going fast, it just wants to keep moving. It wasn't long before I had to jump off.
That was amazing.
All right, that had a lot of kinetic energy.
That was a ton of kinetic energy.
There you go, Science Max, experiments at large, massive spool racer. Your turn next?
Yeah.
Okay.
Science Max! How do you max out an egg drop? With pumpkins, of course. This episode is all about dropping pumpkins and looking at material science.
Knee pad pumpkin!
Cutting edge materials, hagfish slime, ugh, and not so cutting edge, foam. All on this episode of Science Max, experiments at large.
Hey, Science Maximites. Today, we're doing the egg drop experiment and oh no. Oh no! Ha 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 ha. Things like this egg carton are designed to cushion the eggs in case it accidentally gets dropped or in case you want to stack something on top of it. The egg drop experiment is a great way to design some really cool stuff, and it's easy to understand. You take an egg and you drop it. So, let's get designing our egg drop experiment. First, you're gonna need an egg. No! Why? Everything's fine. 1, 2. Right, so where were we? Yes, you need an egg. And you need an adult's permission just in case you make a mess. Now, there are 2 ways to approach the egg drop strategy. You can cushion the blow, or you can slow the descent. And there's tons of ways to do either of those things. Cushioning the blow, pretty easy. You get a whole bunch of soft stuff that the egg can fall into so it doesn't break when it hits the ground. Or slowing the descent, you do something like this parachute idea, and it slows the egg as it falls so it doesn't hit the ground with as much force. And you see, the egg is totally fine because it went slowly to the ground. Now, this episode isn't just about dropping eggs. It is about material science. The kind of materials that you use make a big difference. Styrofoam, tissue paper, very light plastic, very light string. If we were to say use different materials for our parachute version, say wood instead of styrofoam and heavy string and very heavy fabric, I wonder if this would work as well. No, it doesn't. So there you go, Science Maximites. Materials make a difference. And that's what this episode is all about. Material science. Cutting edge materials, new materials, and dropping a whole lot of things to see if they break. But first, I need an expert to help me. Let's see. Who should I pick? Jenna from the Ontario Science Centre would be great at this. Okay. Come Come on. Huh? Hey, Jenna!
Phil, how you doing?
Jenna from the Interior Science Center is gonna help me max out the egg drop.
Yes, but we're gonna need an egg, right?
Yeah, no, I had one when I came through the door. Whoa!
Woo! So do we have some more eggs?
No, that was the last one. But that's okay, because I think we should max out the egg drop, so we need something larger than an egg.
How about pumpkins?
Pumpkins, great idea.
And now we need somewhere to drop them from.
Oh, I already know that. We should drop it from up there.
I think we're gonna need a control group, a control pumpkin. if you
A
will.
control group. You need that in science.
Right, if we're dropping pumpkins and we have nothing to compare it to, then we can't make appropriate observations.
Right, so we just drop a pumpkin straight to see what happens.
Yeah.
Awesome, so we'll get a whole bunch of pumpkins,
Yes.
and we'll start building.
Yeah, let's do it.
And then we'll also probably need to clean this up. Wait, I got a mop over here.
This is our control pumpkin. A control in science means a version you don't experiment on, so you can compare the results of your experiment. So this is what a pumpkin does when dropped with nothing to cushion the fall. Jenna and I really have our work cut out for us because a pumpkin has a lot more mass than an egg, which means it's going to be much harder to stop once it's moving.
So now all we have to do is come up with a couple ideas to stop that from happening.
All right, let's do it.
Science. Yeah. You want the best material around? Well, you come to the right place. I've got them all. I got you flubberoid, magnoplex, flexoweed, pastotherm, bluebifoam. You need hydrogelatinous substrate? I got it. But you know, all those fancy materials are nothing compared to the good old-fashioned spider web. Huh? Hey, where's Gary? Ramona, Gary got away again. You know, people ask me, Sal, is it true spider webs are stronger than steel? And I tell them, it depends. When you look at a rope or a thread or a fiber, you talk about its tensile strength or its ability to withstand force before breaking. But you're comparing different things, so you have to compare them by thickness. So if you're comparing a steel cable to a spider web of the same thickness, then yes, steel is stronger. But spider web is 6 times lighter than steel. So if you are measuring strength to weight, spider web wins every time. Gary! So why don't we build more things with spider web? Well, for one thing, it's sticky and difficult to work with. Almost finished knitting the spider web sweater. It's only gonna take me about 80 more hours. And it's not easy to train spiders. Okay, Steven, one long, non-sticky thread and you get a cookie, okay? And, hey, where's Marco? And Petunia. Huh? But no need to train spiders now because modern science has surpassed the spider web. Enter carbon nanotubes. Huh? This thread doesn't look like much, but it is made of tiny little tubes made of carbon atoms. Think of them like a straw, but a really long straw. Carbon nanotubes are incredibly light and strong. Remember when we compared strength to weight? Well, steel is heavy. Spiderweb is about 6 times stronger by weight, and carbon nanotube is about 50 times stronger than that. That's so great. So why aren't we making everything out of carbon nanotubes? I'm gonna knit a carbon nanotube sweater. Well, first we have to make them cheaply enough to be affordable. There you go. One carbon nanotube sweater. $480,000. But material scientists all over the world are hard at work trying to find ways to make carbon nanotubes faster and cheaper. And soon, they'll be everywhere. And then spiders can go back to spinning their webs in peace. There you are, Gary. Where's everybody else? With Petunia and Marco and... What do you mean they're in my jacket?
Jenna and I are coming up with solutions to the pumpkin drop. We have 3 material science strategies. Strategy 1, polymers. Something is a polymer if it's made of long chains of molecules. Everything in this category is a polymer-based solution. Rubber and elastics are polymers, so I thought, what about a trampoline?
Look to the left a little bit.
My left or your left?
My left. Alrighty, here we go.
And it works great. The pumpkin totally survives until it lands from the bounce.
That's it, like it's a success and a failure.
Balls are made of polymers like rubber or plastic. So how about a bag of balls?
There's the pumpkin. Whoa! I think that worked. Whoa, mostly unscathed.
Almost there, almost there.
Right.
Bungee cords are made from elastics, which are a polymer, and it worked, I think. I mean, it stopped it from falling, but never made it to the ground, unless we unhooked it.
Technically, it survived better than any other pumpkin, really. Here's another polymer solution. This is cornstarch mud. It's a liquid, but if you hit it, if you impact it, it turns rigid.
Right, so that could protect the pumpkin.
Oh, yeah. And now,
The rest.
we add more cornstarch. Cornstarch mud strategy.
But it turns out hardening on impact doesn't cushion the pumpkin much.
Yeah, a bit of a problem there.
I don't think this worked.
And every scientist's favorite polymer,
Giant tub of slime!
Where did you get a giant tub of slime?
Episode 6. All right, let's check it out. Little slimy, all awesome.
now let's recap. This is our control pumpkin, so solutions work if they do better than that. Trampoline? Yes. Then no. Bag of balls? Yes. Bungee cord? I think we need to disqualify that one. Cornstarch mud? Barely. Slime? Yes. Not bad for our first round.
Science!
Advanced materials in 60 seconds. Scientists and engineers are always coming up with new and advanced materials. Some are for spaceships, and some are just for fun. I'll show you a few. Hold on. Like, oh, this. This is a thermochromic mug. It's cool right now, but if you add hot water, it changes color. Ooh, this spring is made out of nitinol wire. It's also called memory wire, and I'll show you why. The reason it's called that is because it's a metal that remembers its shape. This one remembers being straight. All I have to do is drop it in hot water and it turns back into a straight wire. How cool is that? Ha Science! Oh, this is ulexite. It's sort of a see-through rock, but it's made of perfectly aligned crystals. So it's not just see-through, but the image actually gets transmitted from one side of the rock to the other. Advanced materials are really cool. I can't wait to see what science comes up with next.
Now it is time to talk about an amazing natural polymer. It is hagfish slime? Ugh. Still, well, hagfish, that's probably just an unfortunate name for the fish. I'm sure the fish itself doesn't. Ugh. Okay, so hagfish makes slime, apparently. When a hagfish is attacked by something that wants to eat it, like a shark or an eel, it secretes a tiny bit of a natural polymer. That's this little white bit right here at the end of this test tube. Now, it doesn't look like much right now, but it reacts with seawater. Watch this. Hagfish slime is very interesting to scientists because you start with just a tiny little bit and add seawater, and suddenly you have a lot of slime. Whoa. This stuff is actually pretty cool. Hagfish slime is a natural polymer. It's made just the same as the other polymers out of long chains of molecules, but it's naturally produced by a living organism. And because it's naturally produced, that means it's biodegradable. Hagfish slime. It's pretty cool after all. Ugh.
We've had some good successes with polymers.
Whoa, mostly unscathed.
Almost there, almost there.
Right.
Now it's time to try our foam solution. The first foam we use is fruit netting.
Foam fist bump. Boom. See? That didn't feel like
Didn't
much at
hurt.
all.
Which didn't seem like enough protection.
Pumpkin ball. Pumpkin, actually, pumpkin sphere.
Wrapping the pumpkin in a sphere of foam.
Go pumpkin sphere!
It worked better, but not perfectly.
Uh-oh. It split right down the middle.
Pumpkin cube! cube!
Phil?
Yeah.
Phil, what is it?
Wrapping the pumpkin in a cube of foam. Better than our control, but you can see the pumpkin crush as it lands.
Oh, no. Phil?
Totally great! How much did it hold together?
Not at all.
I'll give it 3 cubes out of 7.
We need more protection,
Pumpkin helmet.
which leads us to a bike helmet solution. Which worked the best of all so far.
Totally survived!
Oh my goodness!
Yes, I know, this pumpkin's a bit smaller than our control pumpkin, but our big pumpkins wouldn't fit inside helmets, and we figured it was only a fair test if we used a pumpkin the size of your head.
This is why you wear a helmet, Science Maximites. Look at that. Unharmed.
Expanding foam sealant.
And we spray it all the way around the pumpkin.
Expanding foam sealant is special stuff used to insulate gaps and cracks in the walls of your house. It comes out of a can soft, but then expands and hardens to foam.
A full pumpkin completely covered in expanding foam!
Turns out this stuff is made for insulation, not absorbing shock.
Our beautiful foam pumpkin.
I don't think it worked that well.
So now we recap our foam solution. Fruit netting. No. Foam sphere? Yes. Foam cube? No. Bike helmets? A big yes. The only perfect pumpkin yet. Expanding foam? No.
So that's it for our foam solution.
I think we should move on to armor now.
Yeah, all right.
Foam.
Foam.
Foam. How can they all be foam? Well, foam usually means something to do with bubbles. There's all kinds of solid foams out there, and they can be squishy or not squishy. And they're usually light. Air is an insulator. That means it does not conduct heat or cold very well. You see, I cannot tell this ice is cold until I get my finger really close to it. Yeah, there it is. There, I feel it. And because foam is full of air bubbles, it makes a great insulator. That's why we make coolers out of foam. So what's the best, most advanced foam out there? It's this. It's called Aerogel, and it's 98.2% air. It is super light because it's mostly air, and it's a great insulator because it's mostly air. It's great to pack things in as well, and NASA uses it on the Mars rover and in spacesuits because it's such a good insulator. Cool. Or not cool because, you know, it's an insulator, so it would protect from the cool. We've tried polymers.
Little slimy, all awesome.
We've tried foam.
Uh-oh. It's split right down the middle.
Now it's time to try armor. Anything that protects the pumpkin in a shell of some sort.
This does not look like armor, Jenna. This looks like pumpkin soup.
Our first solution may not seem like armor, but it's a hard shell and the pumpkin floats in the water. When we drop it, the bin explodes, which slows the pumpkin down a lot. The result? Not perfect, but still, remember, it's better than our control.
So compared to the control pumpkin, that did pretty well.
That was pretty good.
Yeah.
I'll give you that.
What is this?
All right, well, we've got a pumpkin covered in knee pads.
Knee pad pumpkin!
Knee pads are armor for your body. So wrapping the pumpkin in knee pads...
Knee pad pumpkin!
Drop it, Phil!
Didn't seem to make much of a difference.
Maybe it didn't land on a knee pad. Maybe we just missed. We ended up in between the knee
I
pads.
think that must be it. It's looking a little rough.
But using sports equipment gave me an idea for using an advanced material. It's called sorbethane, and it's used in modern sports equipment. It disperses impact. See, watch this. Okay, so I've got a hammer, and I hit the pumpkin here, and it goes right into the pumpkin, right? So, take that. Now I hit it again on the sorbethane, and haha, see? Nothing. So I thought maybe this will cushion the impact. The result? Not bad.
I don't think it dispersed it quite well enough. There is a crack coming right from the hole that you made with that hammer.
Okay, so the hole might have structurally weakened the pumpkin a little bit. So the sorbethane did a pretty good job, actually.
Yeah.
Good thing it is in athletic equipment. That's what it's for.
Carbon fiber is a very modern kind of material.
It's carbon meshed together and then glued down, so it's super strong.
Super strong, and the pumpkin is contained inside. It's like double shields.
Yeah, so can I test how strong this is?
Oh yeah, this is the armor solution, so let's try it out.
Here, we better try it.
Whoa!
But when we drop it, we realized there were too many hard surfaces. And not enough cushioning. But the carbon fiber held up really well. Slowing the pumpkin down and cushioning it is the answer, which leads me to my final solution.
I call it the lunar lander. That's what I was doing. I was coming in, right?
Right.
Yeah.
See, I thought we were supposed to be doing armor?
Yes. So this is armor. I know it looks like foam, but you see armor like in a helmet, it's supposed to crumple to protect your head, right? So
Right.
this will also crumple because it's not just foam, there's wood inside. So the wood is supposed to break and then the foam bends and the whole thing is supposed to cushion the impact of the pumpkin. Ooh.
That looks pretty good.
The landing crushed and broke a lot of the arms of the lander, but the braking cushions the impact.
Oh, what do you think?
I think it's good. I think we're good.
Look at that.
And now the awesome recap. Remember, the difference between doing science and just having fun is recording the results. Water bin? Yes. Knee pads? No. Sorbethane? Yes. Carbon fiber? No. Lunar lander? Yes. So, we've had some successes and a lot of failures, and we've learned a lot of things about different materials. And we have one pumpkin left.
There you go, Science Max Experiments at Large, pumpkin drop. Thank you, Jenna.
Thank you, Phil. That was awesome.
And we still have one pumpkin left. Whoa! Whoa, no, no, no! I got it! I got it! It's fine, everything's
Yeah,
fine.
it's fine.
It's,
fine.
we can
I got
take,
this. I got this.
Yeah,
It's
we can
fine.
take that up.
Yeah, no, it's
you got it. You got
good.
it. Careful!
Oh well.
Oh, okay, well.
Make that 0 pumpkins left.
Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, Experiments at Large.
Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in 2 ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. 2 great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxidrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator! Feel the chill of the refrigerator.
All right!
And last but not least, the, regurgitator!
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind the small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law.
no, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later. We're not
opposite
doing this bit now. We're doing that bit in a minute, so we can. No, I said we're doing it later. We're doing it later. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor. probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon power car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
You did.
You did let it go.
It's let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, you okay?
This is why you wear protective eyewear. Yeah. So that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's a
they
good
can hold the
idea.
tanks, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity, he gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart. This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized
I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. Oh, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third.
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right.
Good.
So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked.
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use 2 balls. I swing 2 balls up, and 2 balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls. And I think it's gonna work the same way. Let's find out. You throw one out, and haha! Yeah, it works the same. Okay, now let's try it with two balls. Okay, ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh. Ah!
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube,
Yeah.
and you can see that each tube goes into this one main tube. So when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks. Thanks, Reed. Up so that will push, the pipe will push against the cinder blocks, and then I'll go that
forward.
way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Yeah! Woo! Uh-oh. Woo-hoo-hoo! That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law. Science Max!
This episode of Science Max is all about earthquakes.
Exciting.
How do we build something that won't fall apart when shaken? Plus a lot of other ways to shake things or build things.
Science!
All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when 2 plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... 2 books, 4 elastic bands, and 4 rubber balls. Oh, wait. Okay. 4 rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put one set on one side, one set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books in the middle-ish area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do.
You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books.
And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Oh. And there it goes. And when you've done that, what you do is you be a science maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there. And then we shake it, and we see what happens. Oh no! Oh, there it goes. So that is what we're going to be doing today on Science Max Experiments at Large. We're gonna be making a giant shaker table and putting a giant structure on top and seeing how we design it to make sure it stands up to the shaking of an earthquake. I'm gonna need an expert to help me though. Oh, I know, Anne would be really good at this. Okay, all I need to do is get Anne, and we can start. Oh, come on. There it is. All right.
Hey, Anne, I feel weird. Why do I feel weird?
I think you're a chair.
Well, that's not good. Hold on a second.
Am I good? Okay. Hi, Anne. Good to see you. Here's your lab coat.
Thank you.
So you're from Let's Talk Science, right?
I am.
All about science education, just like us. Today, I need your help to max out our earthquake table. This is the table
This looks
part,
great.
obviously, but this is a tower I've made out of popsicle sticks. So in order to max it out, I've already built a large shaker table. Come on. This is my large shaker table. So it's got basketballs underneath as the 4 balls, but it works exactly the same. Whoa. Whoa. Okay, so what kind of tower should we make for the shaker table?
If we want something tall, then we'll reinforce it a couple spots. But the true test, it's gotta have some sort of weight on top so that it will mimic the weight that would be on a real tower.
Right, so maybe I could get a plastic bin and I'll just put some sandbags for weight inside.
That would be perfect.
And then balls, so that when it falls over, the balls will go everywhere.
That would be perfect.
Okay, great. Shake off. I don't know. I think we should just get off. Another thing that happens during an earthquake is soil liquefaction. Liquefaction means something turns to liquid. In this case, the very ground you might be standing on. Here's how you can experiment with soil liquefaction. All you need is a plastic container and some water, not very much, barely enough to cover the bottom of the container, because what you're gonna put in next is sand. And you wanna put it in there and spread it around. Just add enough sand so it just starts to turn dry on the very last layer. So here is a house that I'm going to put on top. And now I will simulate an earthquake. The water rises up and it sort of turns to liquid. Soil liquefaction. And heavy things like houses and cars, they tend to sink like that. And then the soil rehardens and everybody's houses are stuck in the mud. Now, let's max it out. This is a giant tub of sand and water, and this is a vibrating platform that will simulate an earthquake. Now, as you can see, this sand is totally solid. I can jump all around on this sand, no problem. But when I turn on the vibrating table and simulate an earthquake, things will change.
The vibrations bring the water below the sand to the surface and cause the sand particles to separate. What was solid now turns to liquid in my simulated earthquake, and I start to sink.
I'm up to my shins! And there you go! Soil liquefaction! Hey, look at that! It's totally solid! Woo-hoo-hoo! Soil liquefaction! I'm totally... Uh-oh. You know what I realized? When it stops vibrating, it really becomes solid again, and it's very tough to... Well, there you go. Soil liquefaction. I'm really kind of stuck in here.
So Ann and I have made a large shaker table. Now it's just a matter of designing a building. We use lumber and cut it up, use screws to attach it all together, put a platform on top for a weight, and attach it securely to our shaker table. The building is super simple, just 4 corners and a few planks around the outside. No structure in the middle. And finally, the big heavy weight on the top.
There.
We attach a pole to the shaker table so we can shake from a safe distance and try it out.
Okay, very slow.
Forward.
Let's see how much shaking it can stand with our shakeometer.
That seems to be okay.
Kidding.
Oh no.
We barely start to shake our tower before it collapses.
Oh, that didn't really last very long, did it? It completely folded up on itself. What do we do to fix this, make it better?
I think the easiest thing we can do is to use thicker wood. It'll make it less wobbly.
Okay, sure, let's make another one. High fives. We do have lots of wood, that's a good thing.
Ann and I are trying small improvements every time.
There.
Our last building used thinner pieces of wood. Now we're using thicker wood, which we think will help keep the weight at the top from collapsing the building. Everything else about the design of our building is the same. We put the weight on top and fix our pole, and we're good to go.
All right, you ready?
Okay. Starting to creak.
But it recovers. You can see it lean, and then it comes back, and it resets.
Definitely doing better than the last one.
Oh, no. I'm impressed.
Uh-oh, here we go. But it definitely did better than the first one.
It did better than the first one.
And the thicker wood definitely helped.
But it was really starting to turn.
I think on the next one, we need some platforms in the center to help strengthen it even more.
Earthquake Building 3.0. Thicker wood this time, but with platforms in the middle.
So we're gonna see how well this version works with these middle parts that'll hopefully reinforce.
And they're just like the floors of a building.
Okay, well, let's find out if it's gonna make any difference.
Starting to wobble a little, but it looks pretty good.
As soon as we start shaking, it's really obvious this building is more solid.
Uh-oh, starting to creak. Oh, it's really starting to creak.
The platforms in the middle really seem to improve the structure. You can see it bend all the way over and still recover. But still, it wasn't long before...
Really starting to lean.
Wow, the extra pieces really kind of made it more impressive.
It definitely lasted a lot longer than the other two.
It did, but here's what I'm wondering. Are we going in the wrong direction?
What do you mean?
Well, because if it's really solid, it resists the change.
Okay, I see where you're going with this.
So if we make it flexible, it can resist the shaking of an earthquake.
I think it's worth a shot.
Yeah, okay, let's do it.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. My tuna fish and meatball sub soup is coming along quite nicely. But what will we have for dessert? I know. How about earthquake buildings? Ha ha! It's a building made out of wafer cookies. But the people on Vanilla Street built in the gelatin neighborhood. And the people on Chocolate Street built in the crispy rice part of town. Exciting. Now, here comes the earthquake. Oh no! Oh, it's shaking! Oh, the shaking is come and gone for the people on Chocolate Avenue, and their building is still standing. Now, let's take a look over here on Vanilla Street, and here comes an earthquake. Oh, no! Oh, dear! Looks like the people on Vanilla Street are going to have to rebuild their building because it's all fallen over and being eaten. Delicious. Buildings can be built the same way, but the kind of soil they sit on make a large difference if there's an earthquake. Shaky, wiggly soil or solid, non-moving soil. So there you go, an experiment you can try at home. Delicious. Well, I'm Buster Beaker, and thank you for joining me on this episode of Cooking with Science. Now to try my soup.
Seismometer in 60 seconds. Learning how to predict and measure earthquakes is an important branch of science. The Earth is shaking, but which way did the earthquake come from? It's all about measuring the vibrations, and to do that, you need a seismometer. All you need is a ball, some paper cups, some modeling clay, a pencil, and science tape, which is the same thing as invisible tape, except I use this tape for science. First, take your pencil and stick it straight down into the modeling clay. Then, you take your cups and you arrange them in a circle and tape the cups down. And that goes right in the middle, just like that. Now what you do is you take the ball and you carefully balance it on the pencil. Now you have created a seismometer. It will tell you what direction an earthquake came from. Watch, I will be the earthquake. Ready? Did you see that? The ball fell into the cup facing the direction that I hit the table. And now I'm gonna hit the table from over here. Yep, it fell in the direction that I hit the table. Okay, let's try from over here. There you go, your very own seismometer that you can use to measure earthquakes that you create on the table.
Back to our earthquake building. Ann and I tried a few different designs, and they each got a little better. But now we're wondering what would happen if we built the tower out of very flexible material. We used some plastic tubing and attached the wood with bungee cords, which are like big elastics.
Wow, okay, so looks good.
So let's test it.
Okay.
And sure enough, when we start shaking it, the tower holds up to as much shaking as we can give it.
Wait,
What?
aren't we missing something?
Oh. Yeah, we're missing the weight at the top. Of course.
So I think we need to try it again.
So we add the weight to the top, and then everything changes.
Oh, no.
Look at it twist.
Oh, dear.
It's twisted. It's
A
gonna
flexible tower is great until you try to put a weight at the top. And then it just seems really unstable.
Oh! Look at that. It's totally bent.
It didn't break at all. It just fell over.
Yeah, it couldn't even support the weight.
So it was almost too flexible.
So I guess we should go back to a more rigid design. But what if we change the shape a little bit? 'Cause you know what I was thinking? This is a very stable shape. Triangle, because triangles are really strong. What about we make an X?
Like a triangle within a triangle.
Triangle, and then triangle. So that really reinforces all of the shaking, like all of the motion.
We'll never know until we try.
All right. Uh-oh. I have all my friends coming over, and I don't have a table. But that's okay. I will make a table using my friends. This is an awesome experiment you can do with 4 friends. Come on in, science friends. I've got Sam and Dylan and Polly here to help me. So everybody turn to your left and sit sideways on the chair, and then scooch the chairs into the middle. And then everybody leans back onto the knees of the other person. And then, this is why I said you need 4 friends, because you need the 5th person to remove the chairs! Whoa. The reason why this works is because everybody's weight is being supported on the legs of the person next to them. Okay, we're gonna rotate in a circle, everybody. Okay, ready? Here we go, rotating, rotating. Oh, science table. Ooh, hey, we're pretty good at this. Okay, uh-oh. Oh no, oh no! So there you go. Awesome way to make a table using your friends. Well done, science. Here's an experiment you can do to impress the adults in your house. You need 3 glasses, all of equal height, and 3 knives, not sharp knives, the dull knives you use, maybe the ones you use at dinner time. Take your 3 knives and put them in a triangle, all equally spaced out. Then move the knives together to make a little triangle, right like that. Then what you want to do is you want to carefully arrange the knives so each knife is going above one knife and below another knife. So there we go. Then you want to take this careful pattern that you created and you want to put it on top of your 3 glasses. One where each handle of the knives are going to be. And if you place it carefully and you've done the over-unders correctly, it will stay up. Pretty amazing. The knives support their own weight. But they don't just support their own weight, they can support a lot more weight too. Pretty amazing, right? This is a great experiment. It's also something really interesting that we can max out. Come on. And here you go, the maxed out knife balance. I've got 3 pieces of lumber and 3 barrels, and as you can see, the pattern is exactly the same. Under, over, under, over, under, over. Ha-ha. So, the question is, how much faith do I have in science? It totally supports my weight. I know it's going to work because I know that a 2x4, which is the kind of lumber I'm using, can hold up my weight. So that means the structure can support me. Science! You know what the cool thing is? The cool thing is that even though it's holding me up, each one of these pieces of wood is only up because it's supported by the others. You pull one out and it all falls apart. Ann and I have tried solid towers and flexible towers, and nothing has worked fantastically yet with a big weight on the top. Having a big weight on the top of our tower means we need something that will resist the movement of that weight. So now we're going to start with a triangle. Unlike a rectangle, triangles are very stable. A wider base keeps the structure from swaying too much. And cross braces in the middle mean that there are other triangles within our triangle, all the better to resist movement. Thank you. After Ann and I built our tower, we added the weight to the top, secured it to the base, and tried it out. Okay, here we go. Ooh.
Looking good.
No problem.
It's not twisting.
It's
not leaning.
Not even creaking.
No, it looks really good.
Wow, this one is really solid. As you can see, this tower is way more solid than our square tower or the flexible tower. Okay, look at that. Like, if that's not an earthquake, I don't know what is. Look at that. Look at the way the ground is moving.
I don't know if we can shake it much more than this.
Faster. Our triangular tower is up past a level of shaking that made the other towers collapse. Now it's time to max out the shaking. There's only one level of shaking that we can do above this.
What's that?
We shake from either side. We give it all we have. The floor was bouncing from side to side, the tower was tilting, and was totally solid.
It's still holding strong.
In fact, Ann and I wore out before the building showed any signs of falling over. I think we've done it.
Woo! Nice job.
Nice. Science Max experiments at large, earthquake-proof building. I mean, come on. That was impressive.
I like it.
Science Max! Today on Science Max, we're using the forces. Pendulums are pretty simple. It swings back and forth. Marbles, dominoes, sledgehammer, trebuchet, rockets, levers, rockets, tension, and that's just the main experiment.
Maxed out dominoes.
I love that idea. All this and more on this episode of Science Max Experiments at Large. Greetings, Science Maximites! My name is Phil and welcome to Science Max Experiments at Large. Today we're going to be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're going to look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machine! Rube Goldberg machine! Rube Goldberg machine!
machines! Rube Goldberg machines! Rube Goldberg, you heard me say Rube Goldberg machine. Okay, we got that part? Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out. It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off, and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay. Hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1. Sonia!
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble, and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia. Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You want to try it? Yeah, please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go.
The
Why didn't
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes, I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will see.
Do they dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay, so
we
now.
started off with this domino. Then we went bigger.
Yeah.
Bigger, 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 bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then...
Here we go.
3, 2, 1. Whoa!
Nice. That was pretty far.
Yeah, check this out. Whoop. Okay, so
Nice.
now that we've got the trebuchet firing, the ball is going over there. We need to get the ball going over here to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over.
Okay.
Now we're gonna talk about tension. What's tension? One more than 9-shin. Get it? Because tension and 9-shin, that's, okay, because tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these nuts. And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science.
Sonia and I are maxing out a Rube Goldberg machine. The first part worked pretty well, and now we need to change the ball's direction.
This is a trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way.
The one thing you need most of all when making a Rube Goldberg machine is patience.
Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So, not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap,
Oh.
and...
Ah, so then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
Yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. When it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that! Whoa! Super maxed out! Science! Sonia and I have used potential energy, the lever, and chemical energy. But you know what one we're missing?
What?
Is electrical energy. Electromagnetism. So watch. The chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall and flick this switch. See that sledgehammer?
Uh-huh.
This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready?
There.
There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try
let's try it. Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked. The chemical rockets fire, and they hit the tray. All right?
That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, button, cake.
I have an idea.
All right. Cake any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back, as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. Sonia has added one more step to our Rube Goldberg machine, a stomp rocket. It's a hammer rocket.
Exactly.
I like
so
that.
what's going to happen is the hammer is going to hit our bottle, which is going to release all that air that's built up inside of it. It's going to hit that button.
Wait. The rocket hits the button.
And then we get some
cake!
Cake!
Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1. Oh. Let's pause here just before the cake portal's in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever, with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap, which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our stomp rocket with it. The stomp rocket flies through the air and hits our cake button, which then portals in some cake. Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
But
let's go.
Science Max! Taking something flimsy and making something strong. Whoa, pasta bridge! We build things out of pasta, sand, and paper to show how you can use science to make something strong out of something weak. Dry sand, wet sand, science sand. It's all how you build it. Today on Science Max, Experiments at Large. Oh, hi, Science Maximites. Have you ever been eating pasta and wondered, what could I build with this? Could I build something that could hold an impressive amount of weight? Well, I have, and that's what we're gonna do today on Science Max Experiments at Large. But we're not gonna use cooked pasta because it's too delicious. We're gonna use uncooked pasta, which is less delicious, but it's great for building. We're gonna make a pasta bridge. Here's how you do it. First, you wanna start with a plan. And then you wanna take your pasta, I'm saying pasta, but of course spaghetti is usually the best thing to use, and lay it out on your plan. The reason you have a plan is so that you can make sure all of the spaghetti is exactly the right length. Lay it out on your plan, perfectly aligned like that. There. And now it's time to glue it all together. Now you can use white glue, but it takes a long time. So I suggest a hot glue gun, but make sure you get an adult's permission before you use one of these, okay? So you take your plan, you lay it out, you glue it up. Don't glue it on the paper because that will be bad. And you will end up with your truss, and it looks just like this. Now remember, you want 2 sides because those are the sides of your bridge. And as you can see, I've used several strands of pasta because that'll make it a little bit stronger. Once you have your trusses, it's time for the next part of the plan. This is the roadway, and it works the same way. Lay out your pasta, glue it up, and bam, there it is. Now, you put your trusses on your roadway, and you glue them all together, and you also want to put some struts along the top here, probably, to keep it nice and rigid. In the end, you will end up with a fantastic looking pasta bridge. Pretty good, huh? Pasta bridge. No other bridge could claim to be 100% pasta, minus the glue. 99.8% pasta, 0.2% glue. I say there, Captain. Set sail. Set sail for the land of pasta bridges. Now, if that was pretty fast for you, don't worry. All the instructions are gonna be on our website. Now, a bridge isn't a bridge unless it spans a gap, because that's what bridges are for. So you put your pasta bridge up there across the books like that, and then you can see just how much weight the bridge holds. It's pretty impressive. If you build it right, even something as flimsy and as delicate as pasta can hold quite a bit of weight. I like to use big, heavy blocks and put them in the middle where there is no support from the books whatsoever, and just keep adding heavy things and see how much weight the bridge will hold before it breaks. How much will it hold? Well, I'm not gonna tell you. That's where you get to be Science Maximites and find out for yourselves. And now, we're gonna max it out. Today on, oh, my pasta. Today on Science Max Experiments at Large, we're gonna be looking at how fragile things can become strong if you build them right. We're also gonna be maxing out the pasta bridge experiment to see if we can make one that's strong enough to hold me. You think we can do it? I know I have no idea, but I'm going to the Center for Skills Development and Training to find out. Oh, hey, Kyle.
Phil.
How you doing?
Great, thanks.
Awesome. This is Kyle. He's got a master's in civil engineering. Did you want some pasta?
I'm good.
I can go back and get some more.
Really, I'm good.
Okay. So what does a civil engineer do?
Well, a civil engineer builds the world around us. Talk about our homes, keeping us warm in the winter, our roads, hey, even our bridges.
Bridges, that's fantastic, because that's what I need your help with. I want to max out the pasta bridge.
Awesome.
I want to make one big enough that I can walk across it.
Okay, that's never been done before.
I know, right? You think we can do it?
We're gonna need a lot of help to do that.
We don't need help. All we need is a lot of pasta, which I have. Ha-ha!
Nice.
What do you say?
Yeah, let's give it a shot.
Okay, we'll give it a shot. Why don't we just take some to start, and then...
In order to max out our pasta bridge, the idea is to take many, many strands of pasta and just keep gluing them together so the long beams of pasta in our giant bridge is nothing but many, many regular-sized strands of pasta. Here's where we were after 20 minutes of gluing.
There, that's nice.
Yeah, I think this piece is done.
Okay, so how does it work? Is it strung? Whoa.
Well, let's give it a go, eh? Yeah, I think this will hold.
Great. So we just need to build a few more of these then, right?
Yeah, that's right.
How many more?
212 more.
212 of these.
More.
212, but it took us like 20 minutes to make this one.
Yeah.
Oh, well, I guess so. I mean, this is Science Max experiments at large. That's what we do. We just keep building, and, you know, I don't have any plans for the next while, so we can...
Phil.
Yep.
I think that there's a better way of doing this.
I would be delighted to know there's a better way. It'd be faster than this.
Much faster.
Sure, let's do it.
Awesome.
I'm just gonna put the pasta back in the bag because it'll
Phil,
get stale.
You don't have to do that.
No, but it'll get stale.
Phil, I'm gonna call in one of my friends. We're probably gonna need some more help with this.
Oh man, that's a great idea. Sorry, that's a great idea because because at least we could get your friend to help clean up.
Better sandcastles in 80 seconds.
Building sandcastles is fun, but you can't use dry sand because it doesn't stay up very well. You have to use wet sand. But even if you use wet sand, it doesn't hold a lot of weight. But if you use sand with the power of science, it does hold the weight. Dry sand, wet sand, science sand. Here's what's going on. Say these ping pong balls are grains of sand. When they're dry, they don't hold together very well. That's why you can't build a sandcastle out of dry sand. But if you get the sand wet a little bit, the grains of sand will hold together a little better because of the surface tension of the water. That's why it's easier to build a sandcastle with wet sand, but they still won't hold much weight. But if you add something that creates even more friction between the grains of sand, like say this sandpaper, it will hold the weight. So here's what you do. Take window screen and cut it into circles. Make sure you get an adult's permission first, okay? Deal? Put in a layer of sand, pack it down, and put in a circle of window screen. And a layer of sand, pack it down, circle of window screen. Then, you guessed it, layer of sand, pack it down, circle of window screen. The window screens are gonna add more friction between the grains of sand and will make your sandcastle strong. Strong with the power of science. And then, you can put lots of weight on it. And there you go, sand with the power of science. Okay, I had to max it out. Let's see how strong science sand really is. Huh? Science!
Our pasta bridge was going to take a long time to build out of individual pieces. So we have a new plan.
Hey, Michaela.
Hey, Phil.
How you doing?
I'm great. How are you?
Good. This is Michaela. She's an undergrad in industrial engineering, right?
I am.
And you and Kyle have a new plan for how we can build our pasta bridge that's not gonna look like this.
Oh, man.
This is the best that Kyle and I could do with 20 minutes.
Okay, well, I have better.
Good, I'm glad. How are we gonna do it?
So, instead of that, we're gonna try something like this.
Oh, okay. This is sort of like a giant burrito kind of thing, right?
Yep,
But we're going to build the bridge out of this.
exactly.
We're gonna make it longer, though?
Yep, we're gonna make it 8 feet long. We have this long pole, right?
Yep.
And we have sheets of this pasta. We're gonna put them on the diagonal,
Okay.
and we're gonna roll it, but we're gonna start from this corner, and we're gonna keep rolling.
And don't forget to add water.
And we gotta add water.
I'll add the
'cause-
water.
Okay.
Adding water, just like this?
Yep. It helps the pasta to stick together. So as we're rolling, we're rolling, we're rolling. We're gonna keep doing this with a bunch more sheets so that it gets really, really long, like 8 feet long. And when we're finally done rolling, we gotta spray it with some varnish,
Yep.
and so it all holds together.
Great, and then it's gonna be about this thick
Yeah,
when we're finished with it.
exactly.
This is gonna be one of the parts of the deck of our bridge.
Great, so each one of these large pieces is gonna be like one single strand of pasta and the little bridge with it.
Yeah,
We need a lot of these.
a lot.
A lot.
Yeah.
Still, it's a lot faster than doing it piece by piece with just the spaghetti.
Oh.
Every time I hold it up, you make that noise.
Oh. Oh. Oh.
Awesome. The shape of something makes a big difference in how strong it is. Get some toilet paper rolls and put them in a square, and then stack books on top of them. They can hold weight. Thing is, they can actually hold a lot more weight than you probably think. In fact, the amount of weight just paper in a tube can hold is really kind of impressive. Ha-ha! And now, let's max it out. Phil's weight on 2 toilet paper rolls. Nope. Bill's weight on 4 toilet paper rolls. Nope. Bill's weight on 6 toilet paper rolls. Nope. Bill's weight on 10 toilet paper rolls. Oh. Ha! Ha ha! Phil's weight can be supported by 10 toilet paper rolls. But what if Phil jumps? Ha 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 ha! Didn't really work.
Kyle and Michaela's plan is to use a long pole and sheets of uncooked pasta. We roll the pasta around the pole and spray it with a little varnish. We roll sheets and sheets of pasta along an 8-foot-long pole, making many layers of pasta. Then we wait for it to dry and remove the pole. What we have is an 8-foot-long hollow tube of pasta that becomes a single piece of the bridge. Then we attach a bunch of these pieces together and use more sheets of pasta to glue them into the shape we used for our small pasta bridge.
We're making our giant pasta bridge by wrapping sheets of pasta around and around the poles using the technique we just had, making a whole large pole out of many, many, many sheets of pasta rolled around each other. And we've made a giant truss. Look at this. This is great, guys.
It's looking pretty good.
Yeah. If I hit it, you think it'd stay together?
No, stop.
What?
This is pasta, not steel. It's only made to just hold you.
Kyle, what do you think are the chances that this is gonna hold me when we build it?
Something like 50-50.
Not bad. Michaela, what do you think?
I'm gonna hope for the best.
Hoping for the best. That's exactly the kind of gray area we like to work in at Science Max Experiments at Large. Experiments at Large, I don't know if anybody's even ever done this before.
Not to my knowledge.
I don't think so.
Which is why we have no idea if it's going to work. Okay, so one more of these, because these are the sides.
Yep.
Roadway, and then the top.
Yep.
All right, let's do it.
While we're waiting, it's a good moment to point out one of the things that makes our bridge really strong. That is triangles. As you can see, the truss, or the side of our bridge, is really just 3 big triangles. Triangles are very strong shapes to build with, and they work great in bridges. Now it's time for Science So Simple, a caveman could do it. This is a caveman. Today we are going to teach this caveman how to build a strong structure. Here are some boxes. Go on and build a shelter, and I'll come back and see how it worked out. No, that's not right. You need to build walls by stacking boxes on top of each other. That's how you build. Understand?
Oh, yeah.
I'll come back later and see how it worked out. Uh-oh. Does that look right to you?
Yeah?
Look at those boxes. They're stacked on top of each other. But if they are in tall stacks, what would happen if you push on the wall? You see? Walls don't stay up if you build like that. Let's try again. I'll help you this time. First, lay out the foundation, where your wall should go. Good. Now let's make the second level. No, don't put it right on top. You need to stack in between. That's how you make a strong wall. Okay, I'll come back later. Nice work. Why don't you give it a try? Looks strong, but you forgot a box. Join us next time when we talk about how to make a door.
Building a door in a wall is hard because how do you make a big gaping hole in your wall without your wall falling over? Well, people have come up with lots of ways to put doors and windows in walls made of stone blocks over the centuries. And you can do this at home with books like I'm doing or with building blocks. Just go up until you're happy with the height and then stack each next layer a little closer to the middle until the final layer touches just like this. And then you take a big heavy book and you drop it right on top. And it's pretty stable. And you've just made a doorway. It works even better if it's part of a wall because you want extra weight on the outside of these books here. So of course, I had to build one that was part of a whole wall. This is the same corbelled arch built out of little building blocks. And as you can see, I went closer and closer together until it meets at the top, and it is very strong. Whoa. Ha-ha! Now, let's max it out.
The kind of arch we're building is a corbelled arch. And the Science Max build team and I are using pieces of wood cut to different lengths.
How high can it go? We can use my head to, no, okay, wait.
It takes a while to get together, but once it's done, it looks just like the kinds of doorways stone buildings had in ancient times.
Ta-da! There you go, a maxed out corbelled arch. We went straight up until we got to these layers, and they got a little bit closer and closer to the middle until the last piece is one big solid piece. And if we built this right, it should be strong enough to hold me up. Yeah! Science! Woo-hoo! Well, it held me up for a minute, didn't it?
We rolled our pasta and constructed one truss. Now we've made a lot more rolls of pasta and connected them all together to make a second truss and a roadway, as well as the cross braces on top. And when we get it all together, we end up with...
Whoa! Pasta bridge!
Pasta bridge!
We did it! We built it. We have no idea how long it will stay up. But it's up. It's doing its bridge thing for now, anyway. I am very excited because, as far as we know, I'm the only one to try to cross a bridge made out of pasta. What do you guys think?
I think I don't want you to be the last person to cross a pasta bridge.
You're absolutely right. But I'm gonna do it. I think we're ready. Yeah?
Yeah.
Okay. Here we go.
Ah!
Oh no! That doesn't bode well for our pasta bridge. What happened here, Kyle?
You put all your weight in the middle of the joist. It snapped.
Uh-huh.
If only there was a way to distribute your weight. Maybe if you crawled?
Do like the military style kind of.
Oh, right, so that I'm putting my weight on more than one spot.
Yeah,
Exactly.
Oh, wait a minute. That gives me an idea. You guys stay right there. I know what to do. I know what to do. I know what to do.
You're coming back, right?
Skis distribute your weight over a large area so you don't sink in the snow. That's what skis do, which is perfect for the pasta bridge.
Come on.
Okay,
Come on.
Carefully.
Uh-huh. Is it working?
It's working.
I hear some cracking.
This might do it.
Uh-huh.
Try to spread your legs apart.
Spreading my
Distribute
legs
your weight.
apart.
Distribute your weight.
Distributing my weight. It's swaying a lot.
Oh, man.
Oh. Whoa. Across the bridge. Woo, high fives. There you go. Science Max, experiments at large, pasta bridge, skis. What more could you want? Maybe a pasta chairlift of some sort. Science Max!
This episode of Science Max is all about generating electricity.
Where do we get this electricity that we use all the time?
We try to generate as much as we can using human power, plus solar energy, tidal energy, wind energy, and more. All you need to do is
Turn the generator.
all on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape,
It's the same as invisible tape, except I use this one for science.
a cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because today on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Oh, Anthony! Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like in a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So you think this is a good size?
I think this is a great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
To red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and I'll
can
turn
start
the
turning
generator.
Now it's time to play. How much electricity did they make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach to the end of the generator so we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5.
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still, a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike, of course. Yeah. So we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out. It goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. 1 on either side, and 1 on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works.
Anthony and I are trying to create as much electricity as we can using just human power. But so far it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand,
It is now a stationary bike. It'll be even more stationary once we screw it down.
and attaching the generator.
All right, the bike generator. Bike-orator. What should we call this thing?
Bike-nomator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get 1 revolution here means a whole bunch is spinning there.
Exactly. The more we get here, the more our generator spins, and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill.
It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay,
All right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang on a sec. I got it.
And maybe we should attach the horn to the next thing too.
Turn it off! It's so loud!
So you want to generate some electricity, but what do you choose to generate that electricity? Hydro, nuclear, coal, solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are 2 plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons.
Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle, and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set.
Uh-huh.
Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah, from something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That would
and then
work.
the rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So, if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelect? We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da, you're creating electricity with the power of hydro. Ha 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 ha, I did it.
Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible.
Okay.
Okay.
Crash mat.
Uh-huh.
Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here.
Uh-huh.
Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter here.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. He's still off by quite a bit.
Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas,
coal power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes!
Okay.
Give me,
You take the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult.
Spinning, rotating, and turning things around. From a giant spinning top, to perpetual motion, to defying gravity, and...
The Magnus effect!
The Magnus effect. It's all about to spin almost out of control on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Whoa. Oh, I better spin the other way. Today, we're gonna be taking a closer look at spinning. Well, all things spinning. Spinning, rolling, rotation in all its forms. And, when things spin, they're subject to a whole bunch of different forces. And some are strong enough to even counteract gravity. So let's get spinning! Whoa. Okay, let's get spinning! We are going to make a gyroscopic whirligig, and it spins, and I don't, which is a good thing. Watch this. You pull the string, and it spins, and it stands on its end.
Why does it stand on its end when it spins? Because of angular momentum, which we'll get to later.
And here's how you can make one of your own.
You will need some craft sticks, string, a small zip tie, a shish kebab skewer, spacers like these wood blocks, and finally some round discs, which you can cut out of plastic or find from parts of broken toys. Now, if you want to research this yourself, look up gyroscopic whirligig.
Get 2 craft sticks and glue them to your wooden blocks just like this, and then do it again.
Space them apart and glue them to crosswise craft sticks, and this will be your launcher.
You put your hand in the small end, and the longer end here is where you put your gyroscopic whirligig. Now let's make that. What you want to do is you want to take a shish kebab skewer or whatever fits the diameter hole of the round things that you're using. I like to use little plastic discs from, these are from remote control mechanisms, but you can use anything you want.
I found that this launcher works best with 4 discs of the same size.
Just like that.
Space them out evenly, glue them down, and cut the skewer even on both sides. Then add your zip tie. Put it right in the middle, tighten it up, and cut off the dangling end. This zip tie just gives you somewhere for the string to hold on when you wind it up. Now for your pull handle. Glue 2 craft sticks and 2 wooden blocks, then 2 more craft sticks on the sides. Then tie a string to the middle, wrap that string around the middle of the whirligig, and...
Aha! You have a gyroscopic whirligig, a pull handle, a rope, and your launcher. Now remember, you put your hand in like this, and you fit your gyroscopic whirligig in just like that, and you pull towards you, and it spins! Oh, and that's what we're gonna be doing today, Science Maximites. We're gonna max out a spinning rig, something like this. It's gonna spin bigger, faster, more weight. It's gonna be totally maxed out. So come on. But first I need an expert to help me out. So, let's see here. Ah, wait a minute. Aha! Perfect. Come on, this is gonna be great. Okay, this is it. Hey, Silita from the Ontario Science Center. I'm really glad you're here. You're gonna help me max out the gyroscopic whirly gig.
The what?
Oh, the gyroscopic whirly gig. Here, I'll show you. It's this, and it spins, and what works on...
Phil, where are your shoes?
I think these are my shoes. They must have changed into flippers in the portal. Weird.
Want to change them?
Yeah, I'll be fine. Anyway, like I was saying, the gyroscopic whirly gig is really good. Let's do it here so that I don't have to walk as far.
Can I see it?
Yeah, here it is. Ready? You spin it up, and it spins, and it goes for a while, right?
Because you made it out of 4 discs, it probably spins better because there's more mass.
Oh yeah, because you know what? I actually have an old one. Yeah, I got an old one here with 1 disc, and it does not spin as long as the 4-disc one.
Could we test the 1-disc one out and compare it to the 4-disc one?
You bet, because you know what that is?
Science.
Yeah, that's science. Okay, let's try it. Ready? Whoa.
Huh, look at that. The 4-disc one spins better longer than the 1-disc one because the 4-disc one has more
mass, therefore more inertia. So when we max it out, we should get something with a lot of mass.
Yeah, more mass.
Wait, I have something. Right. Whoa. Can you give me a hand?
Careful, Phil. I don't want you to fall.
Yeah, well, I don't want to fall either. It's hard to walk in these.
I can imagine. That's why I asked you if you wanted to change your shoes.
We're fine. I'm fine. Okay, check it out. This is what I was going to. Okay, this is what we can make it into our maxed out spinning gyroscopic. Why not?
It's just, look at how big the hole is.
Oh, yeah, because we're going to need something to be the axis, huh?
Yeah, we need like a tree to fill that.
Yeah, you're right. Too big. Is there anything else wrong with it?
It's also kind of light. It's not that heavy.
More mass, better.
More mass.
Okay, tell you what. Oh, I know. Hold on. I know. Whoa.
Oh, that looks perfect.
Yeah, and then we got this pole.
To go through the center?
We'll go through the center like that.
Awesome.
And then we'll just weld it together, and there you go.
This will be great.
Yeah, high five.
Phil.
Okay, no, wait, sorry, yeah, you got the thing.
High five.
Well, now I got the thing.
Yeah.
All right, I'll get new shoes, and we'll work on our high five. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that, and then let them go. They fly up and out. The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath. And that is called the... Oh, come on.
Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No. Max it out. Check it out. Magnus Flyer 2.0 stand elastic slingshot. Wrap it around. Remember, for the Magnus effect to work, your cups need to be spinning this way. The front side rotating up. Oh, and there you have it, the Magnus effect.
I, Magnus, am out taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
Silita and I are maxing out our spinning top.
Based on our small version, we decided to make one with as much mass as possible. So we got a 20-kilogram weight and welded it to a metal shaft. Will this work the same way? Well, let's look at the science. Why does a top spin? Well, let's start with Newton's first law, which is an object at rest tends to stay at rest, an object in motion tends to stay in motion. But the in motion has another part. That object also wants to go in a straight line. If you think of a bowling ball rolling along, it would need another force to act upon it to make it change direction. We say that a moving object has momentum. Now, a top doesn't go in a straight line, it spins around, but it still has momentum. It's an object in motion, and even though it's spinning, it still does want to go in a straight line. It's just that that straight line is here. We call this angular momentum. To make a top move this way, or that way, would take an outside force, so it stays upright as long as it has enough momentum. But when it slows down, there's less momentum and it becomes harder to resist external forces, like gravity, which will eventually want to make it topple. Our top has a lot of mass, which means it'll have a lot of angular momentum when it gets spinning. It's just a matter of getting it spinning fast enough.
So should we spin it?
Yeah, let's spin it. Let's see if we can get it to work. Hey, okay.
Spin.
Oh, we're gonna let go. In 3.
Wait. I can't get it.
1, go.
Wait.
Okay.
Okay. Not fast enough.
We need something to help us get it spinning faster. Maybe a rope?
A rope, yeah.
Wrap a rope
That
around
was
it
my
like the-
idea too, a rope, because the small one uses a rope.
Yes.
Okay.
Okay, I'll go grab a rope.
So, wrapping the rope up.
I'll let you wrap the rope
Okay.
up. I'll get my holder back on top.
Spin it counterclockwise.
We attach the rope and wind it up.
You want to make it super clean. This is some of the best coiled rope I've ever seen. I'm gonna pull the rope. You're gonna hold on to it, but I can't pull really hard because you won't be able to hold it up. Because we don't have to pull hard, we just have to get it going fast.
Yes.
Sailita keeps her hand on the block at the top and I pull.
Ready?
Wait a minute, we'll get all the way. Oh. Whoa!
Spinning a lot better than I thought it would. It's still spinning, but it's wobbling.
Oh, careful.
Oh, there it goes.
It works, but just barely.
It might spin better, it might spin straighter.
Yeah.
If we had it spinning, something help us spin it faster.
Yes, faster with more power.
With more power.
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are 2 motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right, where was I?
I believe you were at, the reason why this works is...
Right, pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then, because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string, science.
Sailita and I need to get our maxed out top spinning faster. We tried a rope, but now we're trying a drill. We get a wheel on our drill and use it on the outside of the weight to get it spinning up.
A little faster.
Oh, it's wobbling now.
A little more.
Push me.
And release. Whoa! It's kind of cool that it wobbles that much and it doesn't hit the ground.
It worked better, but there's always a way to max it out even more.
You know what we need, Sailita?
What do we need, Phil?
A maxed out drill. Put it right on the top here and get it spinning very, very fast. Super maxed out gyroscope
Okay.
whirly gig.
Gig.
Is it just the top now?
I don't know. Do you
We
want to
could
keep
call it
calling
a gyroscope.
gyroscope
Well,
whirly gig?
it's sort of a toppy, kind of gyroscopy. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope, nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Haha, Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remembered to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air.
How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle.
So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor. Yeah! What was that?
It's my science confetti high five I just made.
Well, you know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and more confetti that would come out, right? And then so what would happen is there would be all this Trevor?
Sailita and I have maxed out our spinning top. The trick is getting something that heavy to spin really fast. We've tried a rope and a drill, but now we have a maxed out drill.
So more power and more speed, which is perfect for spinning this massive top.
Yes, and perfect for maxing out anything.
We get it spinning and it works great. The top spins for a really long time. In fact, its mass was so large, it started drilling a hole in the concrete floor. We tried it again, but started to notice something.
The drill is smoking quite significantly.
Our drill began to overheat. Why? Good old Newton's first law. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more mass we have in motion, the longer it will stay in motion.
This will go forever. Well, not forever,
Well, not
but
forever.
it'll go a really long time because it's got a lot of weight.
But that same mass wants to stay at rest when it's not moving. We have to overcome all that mass wanting to stay at rest to get the top spinning. And even for our maxed out drill, that was a tough job. But once it was spinning, there was only one thing to do. Max it out even more! Sailita and I come up with a plan to max out the top by riding it.
You want to ride the top?
Of course I want to ride the top.
We can both ride the top. One person's gonna have to drill this, so we'll have to take turns.
Max Historica. This is Leonardo da Vinci, one of the greatest scientific minds the world has ever seen. And this is a wheel. Da Vinci thought to himself, wouldn't it be great to design a wheel that kept spinning forever? So he got to work. Something that keeps spinning forever without stopping is called a perpetual motion machine. And it was an obsession of Da Vinci's. Why, this is great. The bottles tip the water to the outside, making one side of the wheel heavier, which will keep it spinning forever. Except it doesn't work. You see, what Da Vinci doesn't know is that science says a perpetual motion machine is impossible. But of course it wasn't for another 350 years till scientists figured that out. So we can't tell Da Vinci. What? Oh, never mind. Leonardo da Vinci, one of the greatest inventors ever. Even if not all of his inventions worked. Xylita and I got our maxed out spinning top to work pretty well. The only thing left to do was to ride it. We attached a large disc and a Lazy Susan. That's a platform that spins around on ball bearings.
Lazy Susan on top,
Lazy Susan.
so that you can ride on it.
Yes, and then we wanted to add this extra bit. Now, why did we want to add this?
We need a little bit more weight on our top.
Okay, so who gets to ride it?
I feel like you should ride it.
I think you might be right.
Because I want to use
Oh,
the drill.
the super awesome maxed out drill. Okay, so let's do it. First thing I should say is do not try this at home. We are trained scientists.
Xylita uses the drill to get it spinning while I hold it steady. Then I hold on to our safety line above and carefully rest my weight on the top. It works, but not for long. We take turns trying it out, but it seems we have another part of science working against us. Good old friction. Friction with the air and with the ground is what eventually slows a spinning top down. But our weight on the ball bearings of the Lazy Susan really increases the friction. More friction means the top slows down a lot faster.
Whoa!
That was pretty cool.
It was kind of terrifying, right?
Yeah.
Good old Newton's first law kept the top spinning, angular momentum kept it from falling over, and friction slowed it back down. The forces were always the same, no matter if it was a little top, a maxed out top, or a rideable one.
Yeah! Whoa! There you go, Science Max! Experiments at large, giant spinning top. That's as large a spinning top as I think you
I think in the entire world.
Let's do it again! Yeah!